Now we're going to have you guys start looking at something else. We're going to have you guys start looking at what is called induction. Now, in the previous section, you guys were looking at circuits and using electricity, and this has a lot to do with actually making electricity. So we're going to start looking at induction, specifically electromagnetic induction. Okay. Now, where we can start with this is we can start in the 1800s with a guy named Faraday, who had a whole lot to do with electricity, as you guys know it, and a whole bunch of other stuff. You guys actually owe him a lot of stuff. Now, we'll sort of simulate what he did here. We've got, let's take a piece of iron, something like this, and we're going to take some wires. I'm going to color code these greenish color. And he had wires wrapped around a piece of iron. And you can hook this up to a power supply, maybe something like this. And then there was a second set of wires around the same thing and hooked up to a galvanometer. Now, galvanometer is a device that detects current and stuff like that and moving charge. Let's clean that up a little bit. So it's a galvanometer. Voltmeters and ammeters are versions of galvanometers. Okay, so this is, like I said, this is a piece of iron in here. Okay, so really generally straightforward here. You've got the power supply on the left-hand side, of course, that produces a current that goes through the coils. You guys know this. That's going to produce a magnetic field. So obviously we're going to have a magnetic field in there, obviously. And what is interesting about what he noticed is one of those sort of like this accidental type things, that when he actually put current in the first side over here, he produced a magnetic field, of course. There was a current in the second set of wires. So he could actually create a current in the second side. Now, there was lots of ideas of where this came from. Like, was electricity leaking from one set of wires to the other set of wires? There's a whole bunch of ideas that actually kicked in. We'll get to that a little bit later on how you can actually show that's not true. But it was kind of cool. Now, the only thing is, it only actually happened when the first current was actually turned on or off. Okay, so he would turn on the power supply, he'd have current going through it, and he would get the galvanometer to actually deflect. The needle would actually move. But while the system was actually running, you got absolutely nothing. And then when he turned it off again, the galvanometer would flip again, except it would actually flip the opposite way. So the only time he could actually get this thing to actually do anything is when he turned it on and off. So here, we can even modify this a little bit. We'll throw in a switch. There's my switch. Okay, so the only time anything would actually happen is when he turned the switch on and off, which is really kind of strange. Now, to show that it wasn't just electricity leaking across, another similar setup can be done where you take a piece of like an iron ring, and instead of having like the wires sort of touching each other, you'd have the systems totally separate from each other, something like this. And the second set would be something like this. And you can do the exact same type of thing, and the same thing happens. So it sort of showed it was the magnetic field going through the iron, not electricity leaking from one set of wires to the other set of wires. Like the wires weren't in contact with each other because they were insulated. They didn't have plastic back then, but they'd insulate them with like cloth and stuff like that. So you could actually separate the systems and you get the exact same result, which is kind of strange. So from this, he realized sort of the important part of how this worked. It wasn't actually having a magnetic field there that was really important. He sort of realized it was a changing magnetic field was actually, get rid of that. It was actually the changing magnetic field was the key to the whole thing. That was the important part. It wasn't actually having a magnetic field. It was changing the magnetic field. And this is the beginning of electromagnetic induction. So if we sort of like label a couple things here, on this first side here, we know we've got an EMF. Remember the EMF type thing? We got the EMF on that side. We have current on this side, and they will create a magnetic field inside of here. And then on this side, we end up with an induced EMF and induced current. So we've got EMFs or voltages on both sides. We've got current on both sides. And it's that changing magnetic field. It's this changing magnetic field in here that's the key. That's what binds them together. And we also can kick into another quantity. Remember the quantity flux? Remember that one from electric fields? That's sort of the key. You know, there's electric flux, but there's also magnetic flux. And you can have a changing magnetic field, which then you have a changing magnetic flux. And that changing magnetic flux is what ties the two systems together. Okay, so this sort of comes into basically Faraday's law or idea for electromagnetic induction. I'll sort of like paraphrase a little bit. Basically what he said is the induced EMF, the EMF or the voltage, which of course is connected to the current that you get on the right side, is directly proportional to the rate of the changing magnetic flux. So basically you have the first side here, which is what actually creates the magnetic field, but you need to change this side, you need to change the current, change the EMF, which causes the magnetic field to fluctuate. Okay, so you have that changing magnetic field, which of course creates a changing flux. The flux gets bigger and smaller, that type of stuff. And then that changing flux then produces an induced EMF and induced current on the other side. So basically, if you want to make a new current, it's all about changing the flux. So let me show you a little something on that. We'll show a little simulation here. So here we got a coils of wire and that type of stuff. Here we got a magnet. And right now there's a magnetic field going through the coil, but it's not doing anything. But if you take the magnet and you put it into the coil, you will get a current produced and you'll get voltage being produced. So it's all about having the magnet move. The same way it's all about having different current and voltage here to change the magnetic field here, we can move this magnet in order to actually change the magnetic field. So if we put it into the coil again, there we go, we'll get a little fluctuation. But right now, the magnetic field inside the coil is huge. It's as big as it possibly can be. We've got a massive field in there, but it's not changing. It's not about how much magnetic field you have. It's about how much your magnetic field and flux can change. And right now, it's not changing. So since it's not changing, you get no induced EMF, no induced current. But if I take the magnet out again, there I changed the flux that was in the coil and it produced a current. So you put the magnet in, you get a change. You take it out, you get a change. And if you notice, if you watch the needle, it goes to the left when I put the magnet in. It goes to the right when I take the magnet out. You get opposite effects. Even if I go through, goes one way, goes the other way. Okay, so it's all about changing the flux. Okay, so I can even take the magnet and flip the magnet. There, flip the magnet, changes the flux because the magnetic field is changing direction. So it's all about changing the flux. If you have it in here, you can wiggle it around. It's not changing the flux, so you're not getting an induced EMF. So the key is that. But also the rate kicks in. If I slowly move the magnet, you can get an induced EMF, induced current, but it's really small. If you go faster, it's bigger. So it's not just how much it changes, it's also the rate at which it changes. So time is also really important. Okay, so that's the idea behind electromagnetic induction, what Faraday sort of figured out. All right, that's sort of the keys right there. Now, another guy also came in as well, and Len sort of built on this idea a little bit, but we'll worry about that a little bit later on, one of his major extensions of this, but we can look at some other parts of this relationship as well. So if we sort of bring this in a little bit more and sort of put these ideas together, if you actually want to find the induced EMF and calculate the induced EMF, well, if you calculate the induced EMF, it's all about changing the flux and the rate of. And of course, when you talk about the rate of, that's comparing it to time. So to find the induced EMF, it's the change in flux divided by the change in time. That's how you calculate the induced EMF. Now, we're going to make a couple modifications here to the expression. That's not the only thing right there, but we'll do some modifications, some really simple things. First of all, what you'll typically see from the expression is a negative, and it's about a conservation thing. If you have voltage and current on one side, and you get voltage and current on the other side, One's positive, one's negative, because the system has to cancel out. Conservation of energy, conservation of everything. One's positive, one's negative. So you often see a negative in front. The other thing that you'll often see is a big capital N, and that's for number of loops. If we go back to the simulation here, I can bring this in. There we go. If I do the same type of thing with just 2 coils, the same thing works. And the thing is, it's 2 coils of wire, so you actually have 2 induced EMFs being put together. But here we got 4. It's a much bigger effect. So the number of coils you have has a big effect on what's going on. So that's why with the expression, you'll often see an N in front for the number of loops that's actually being used. Okay. Now for the actual flux calculation, if you remember when you guys did electric flux, that was EA cos theta, and we didn't really do anything with it. Well, it's the exact same calculation for magnetic flux. There's no difference. The only difference is instead of an E, we got to change that to a B, and we got to change that to a B. It's BA cos theta. There's no difference. So we've got magnetic flux is BA cos theta, and that's it. And that's how we can calculate the flux going through it. Now, this may seem a little bit fancy schmancy, but it's actually relatively straightforward and relatively easy. And we'll do some practice calculations with this type of stuff. Now, a lot of this calculation stuff, Lenz had a big part in actually mathematizing it a lot and putting the formula stuff into it, as well as another thing that we'll get into in the next video. But this is the basic idea behind induction. Induction is used for so many things. It's crazy how much you guys actually use it for. You may not even realize it, but you do. Basically, if you've got any electronic action occurring without actual physical contact or circuitry, it's probably induction. Everything from basic metal detectors, when people are on the beach, you get the little buzzing thing, that uses induction. You got to have induction cooktops for stoves, your induction chargers for your phones, even fobs and pass cards and keys and hotel keys and that type of stuff. Swipe things like in your credit cards and your bank cards that swipe, any type. All these different things use induction, where even like security stuff, like the security tags on clothes that beep when you go through things in the stores, or even little tags in books with go through the doors and you have beeping at a library or something like that. There's so many things that induction is used for, and it's all the same basic idea. Involve a changing magnetic field with a set of wires, and it produces currents, it produces other things. Things detect these currents and that type of stuff, and alarms go off, or opens a door, or charges your phone, or whatever it is. It's all induction. So induction is a huge, huge, huge part of our lives, and it all started like 200 years ago, 150, 200 years ago, by Faraday, who was an absolute genius and did some really important stuff to actually do the baseline for all of electronics and producing electricity and generators and motors. It all uses this type of stuff. So this is where it all started. Okay, so in the next video, we'll do some practice with this, so I'll show you it works, and then we'll incorporate a little bit of more about Lenz and how Lenz gets involved a little bit more with some other nature of parts of this stuff.